and he's going to talk us about that today. So Ramon, whenever you want, you have the word.
Okay, thank you, Elena. Let me share my screen. Do you see it well? And you hear me well?
Yes, very well.
Okay, so I'm going to start. Thank you, Elena, for the introduction. Today I'm gonna give a pizza seminar that is a bit different from what we are used to here in the Institute. I'm not gonna focus on very distant objects, but I'm gonna focus on a much closer one, that's the Earth. And in particular, I'm gonna focus on heavy rain and how we can detect it from space using the GPS system. That's the main aim of the ROHP-PAZ mission. So here in the Institute, Estelle is the PI of this mission. Tony Reeves and Santi Oliveras also work in this project. And here I also list our collaborators from JPL, which are also very involved in the scientific analysis of this new observational technique. So in this talk, I'm gonna briefly speak about using the global navigation satellite system for science applications. I'm gonna focus on the radio occultation technique. That's the base for our observations. And then I will explain you the new polarimetric radio occultation concept. That's what we are going to use for the rain detection. And then I'll explain the ROHP-PAZ mission. This is the mission that is testing for the first time this new polarimetric radio occultation concept from space. And I'm gonna give you an introduction about what we did before the launch and what we are doing after the launch of this experiment on board the PAZ satellite. So I'm gonna start talking about the global navigation satellite system. As its name indicates, this consists of a constellation of satellites that are being used for global navigation. So the well-known GPS system, it's one example of one of these constellations. Here in Europe, we also have Galileo. There also exists the Russian GLONASS and the Chinese Beidou, and these are meant for precise positioning and geolocation as their main purpose. How they work, it's a little bit complicated, but it's based on a very fundamental principle, that's time measurements. So when you look and you track one of the GPS satellites, you know when a certain signal has been emitted by the GPS. So you know the time it has been traveling when you receive it. Therefore, you know at which distance, if you assume a certain velocity of propagation for this wave, let's say the speed of light. And so using this, you know at which distance you are from a certain GPS satellite. Then using 3 GPS satellites, you can know more or less exactly where you are. In fact, you need an additional one, so it's a 3+1, because you need to perform additional corrections, but you get an idea of the basic idea of how this works. However, there are a number of things that can affect the interpretation of these time measurements and reduce the accuracy of your geolocation. These could be changes in the velocity of propagation and direction of these signals due to changes in the refractive index, and this is what we call the atmospheric effects. And also, you can have interferences due to the bounce signals that can reflect on the surface or on buildings, and this is what we call the reflection effects. So what for geolocation purposes, it's a source of errors and problems, for us is an opportunity to investigate the Earth atmosphere and or the surface. And this is a cheap way to do this kind of investigations because the source is already there. So GPS satellites are there and are maintained because they are used for other purposes. It's an opportunistic way to perform research because we only need these small instruments like GPS receivers or additional antennas that can be placed on other purpose satellites or scientific platforms. And it's supposed to be long-term, so you can achieve long-term observations because in principle, there will always be the need for a GNSS constellation. So here in the Institute, the Earth Observation Group, we use two different techniques that take advantage of these GNSS signals. The first one is called GNSS reflectometry and makes use of the reflected signals of the Earth's surface to study its properties. And we also use a technique called GNSS radio occultation or polarimetric radio occultation that is based on collecting signals from space that cross the Earth atmosphere, and we use them to study the Earth atmosphere properties, including precipitation. That's what I do. And since I'm only working on this technique, the GNSS polarimetric radio occultation, this is what I'm going to talk about. So let's move to GNSS radio occultations. So the radio occultations is an observational technique that consists on a low Earth orbiter tracking the signals emitted by the GPS satellites while these low Earth orbiters are occulting behind the horizon. So these rays cross the atmosphere when they go from the GPS to the low Earth orbiter, and as they penetrate deeper and deeper into the atmosphere, they bend due to the changes in the refractive index of the atmosphere. So what we use is these two observables, the amplitude and the phase. We actually use the excess phase. That's the difference between the phase that we observe and the phase that the wave would have had if it was traveling in a straight line. And what you can see here in the plots in the right is that even when the straight line going from the satellite to the GPS is below the horizon, so the straight line height, it's negative, you still get some signal. So this is the proof that these signals bend and you can track them even when you are below the horizon. So using these phase measurements, actually what we use is how this excess phase changes with time. We can infer the bending that these rays have suffered. And this bending is then used to obtain a vertical profile of refractivity. And by refractivity, we mean, or it indicates, the deviation of the refractive index from 1. So here you have two profiles as a function of height of this bending angle and the corresponding refractivity profile that we can obtain in the area that it's closer to where the rays suffer its maximum bending. Then, using this refractivity, we can retrieve the thermodynamic parameters of the atmosphere using a technique called variational retrieval 1D bar. And so essentially what we can provide using this technique are vertical profiles of pressure, temperature, and water vapor. And the characteristics of these profiles is that they are globally distributed. So since it's a measurement that is done from space, we can obtain these profiles everywhere. We can obtain these profiles over all surfaces and under all weather conditions. This is because the frequency that we are using is at L-band. And therefore, when they cross, for example, thick clouds, they suffer very little attenuation. This is something that does not happen for other observing systems that try to retrieve these thermodynamic parameters from space, which are severely degraded when they try to sense the regions within thick clouds. These profiles that we can provide using the radio occultations have a very high vertical resolution, and they have a horizontal resolution of 100 kilometers. And these have been proven to be very, very useful and have a high impact on numerical weather prediction models. And actually, this technique started in planetary sciences. So the first spacecrafts that were sent to explore other planets, like I think the first ones were Mars and Venus, already used this radio occultation technique to investigate their atmosphere. And after some point, all the planets in the solar system were investigated using the radio occultation technique, and even some of their moons. And in fact, it was later when this technique was applied on Earth. The first experiments date of mid-70s in the Apollo-Soyuz mission. Then it was in the 90s where these radio occultation payloads were installed on more operational satellites. And it was after 2006, with the launch of the Cosmic 6 satellite constellation mission dedicated to radio occultation, when the radio occultation, when people realized about the very valuable properties of these observations, they were simulated by then into the numerical weather prediction models for most of the more important international weather agencies. And currently, nowadays, more or less, I think that around 100 low Earth orbiters carry a radio occultation payload, including the small satellites or CubeSats that belong to some commercial companies. So this is a brief overview of this radio occultation technique. So now I'm going to explain what's the polarimetric radio occultation technique. So the GNSS polarimetric radio occultation technique is a new technique that represents an enhancement of this standard radio occultation technique that I have just explained, and aims at detecting precipitation, in addition to retrieving the same thermodynamic parameters that we were collecting with the standard one. It's an idea by Estelle Cardellac. She's also the PI of this ROHP-PAZ mission that it's testing this technique for the first time from space on board of the Spanish PAZ satellite, and everything related to the conceptualization, design, and the sensitivity studies were carried out here in the institute. So the idea is kind of simple. It's a minor hardware modification to receive H and V linear polarizations so when we collect these radio occultations, we do it with two linearly polarized antennas, one in the H and one in the V, instead of using the right-hand circularly polarized antennas that are being used in all of the standard radio occultation missions. Then, using these separate H and V, you can recombine them to obtain the standard right-hand circularly polarized, or even you can use them separately and proceed with the standard retrievals of the thermodynamic parameters. Or you can use the H and V independently to detect precipitation. And how we can do that? So first of all, we need to ask, or we need to know how a raindrop looks like. So if you ask Google how raindrops are, so Google Images, and you put raindrop, you will see this tear shape, and that it's very often used to represent precipitation, but that's not true. The actual shape of a raindrop, it has this oblate spheroid shape, which is elongated in the horizontal direction. Therefore, the horizontal dimension is larger than the vertical, and this is due to the air drag that they suffer when they fall. Actually, this horizontal the horizontal dimension is larger than the vertical, and this difference increases with precipitation intensity. So the more intense, the more difference between the horizontal and the vertical dimensions. So in this radio occultation geometry that we are using, the rays, when they reach the bottom layers of the atmosphere, travel almost or nearly tangential to the surface, and this is where we expect to find the clouds and the precipitation. Therefore, the electromagnetic waves propagating through the precipitating areas suffer a phase delay that is larger in the horizontal component than in the vertical. And this is because effectively you are crossing more media in the horizontal dimension than in the vertical. Then, receiving these signals using two linearly polarized antennas, H and V, we expect that we will be able to observe a positive phase difference between the phase collected at the H channel and the phase collected on the V channel if there is rain along the ray path. So this is the concept on this measurement. And if we are able to detect precipitation, we will be able to provide global all-weather, all-surface, and highly vertically resolved profiles of the thermodynamics, like temperature and water vapor, along with precipitation. And this is a unique observational data set that cannot be obtained from any other observing system. And why we want to do that? Well, we have identified a problem that it's the thermodynamics within heavy precipitating systems is very difficult to observe. As I said before, other satellites that try to retrieve thermodynamics from space suffer degradation of their signals when they enter into thick clouds. Therefore, there are very few observational constraints on the behavior of the moisture or the humidity within these heavy precipitating systems. This movement on the vertical about the moisture is driven by convection. Therefore, convective parameterization remains one of the major issues in modeling and predicting deep convective precipitation. And we expect that using polarimetric radio occultation, we will be able to provide more observational constraints to improve how these processes are modeled and, more importantly, predicted in weather models. So now that we know how this works, I'm going to explain a little bit about the ROHP-PAZ mission. So the ROHP-PAZ mission it stands for radio occultations and heavy precipitation on board the PAZ satellite. And it's a proof of concept experiment that's on board the PAZ satellite. And the main aim is to test the new polarimetric radio occultation concept. The PI is stealth. The experiment belongs and is led by the ICE. And we have several international partners. ICE-CSIC is the owner and who operates the satellite. NOAA and UCAR do the first processing of data and distribute all the data sets to the World Meteorological Organization community. And then JPL is involved more in the scientific aspects of this new observational data set. So the PAZ satellite was launched on February 22nd, 2018 from Vandenberg Air Force Base in California. Our experiment was activated a couple months after that. And it's important to say that the PAZ main scientific instrument is a synthetic aperture radar that it's used for imaging, and that our experiment is a secondary payload. This has its advantages, that it's a cheap experiment, because the only thing we had to do was to install this antenna in the back of the satellite. But being a secondary payload can also be problematic, and I will show you why in a couple of slides. So before the launch of the satellite, we conducted several studies. The first one was the sensitivity study. So we wanted to make sure that the expected noise levels were low enough for us to be able to detect the effect of precipitation in these phase measurements. We concluded that the expected observable noise would be around 1.5 millimeters, and with this, we should be able to detect precipitation. We also conducted a field campaign from Puigdesholles in the top of Montseny next to Turó de l'Home. And it was the first attempt ever to collect the HMV linear polarimetric GPS signals for rain detection. The results were good, but we also saw more features than we were anticipating. We had to hypothesize that ice and frozen particles were also playing a role and were also affecting these differential phase shift measurements. And in fact, using these kind of observations from inside the atmosphere can be more challenging than doing them from space. So the results were okay, but we had more questions afterwards than we were expecting. And we also we prepared some of the algorithms that we wanted to use when the data are available. We designed some of the precipitation retrievals, and also we did a very detailed analysis of all the systematic effects that could be inducing a polarimetric feature in the signal, besides rain or precipitations that was our main objective. We saw that a ionosphere could also be inducing some polarimetric features, but in principle we should be able to correct these effects and calibrate them. So the launch was from the Vandenberg Air Force Base in California, on February 22nd, 2018. Here you can see a couple of images when the satellite was deployed from the SpaceX videos. And I had a video that I did there because I could go to see the launch, but I could not make it work here. So maybe I can show it to you later or another time if you want to see it. And yes, after a couple months, the experiment was activated. And this is the first ever recorded polarimetric radio occultation. It was obtained on May 10th, 2018. Here in the left, you have the amplitude. This is the amplitude and after recombining the H and V signals. And this is the raw phase differential phase measurement that we obtain when we compare the phase between the H and the V channel. And if you remember, I said that we expected noise of around 1.5 millimeters. And if you see here the scale, it goes to 2000 millimeters. So at the beginning, I was very scared. But we realized that we had to apply some corrections that relate to the cycle slips that these phase measurements suffer. when they accelerate a lot, then it can be tricky to track them, but this can be corrected, and this is what I show you here in the lower left. And if we zoom in the next to the zero level on this differential phase shift measurements, this is the expected sensitivity, this 1.5 millimeter, and you see how the order of magnitude of our measurements was okay, but we saw there's this trend here, and there's this wiggling of the signal that required further considerations. So now I'm going to talk about the activities after launch, and the most important one is the calibration. So you have seen this trend that we observed in the signal and this wiggling, and this has a very a reason, and this reason is that PAZ satellite was supposed to be launched around 2012, then it was delayed until 2014, and after many delays, ICE-CSIC, the owner of the satellite, decided to change the launcher. So they switched from the previous launcher to SpaceX, and apparently SpaceX places the satellites inside their rockets in a different way than the previous launcher. Therefore, they had to install a metallic structure that you can see it here that sits right above our antenna. And this is why I told you before that being the secondary payload has their bad consequences, and that is that, I mean, they didn't care too much if they were blocking or not our instrument. In this case, they were blocking part of the field of view, and you can see here how this metallic sketch of this metallic structure on top of our antenna. So what we needed to do is a very thoughtful on-orbit calibration. To do this calibration, the strategy was to create an antenna pattern so we can capture and correct all the interferences and features introduced by this antenna. But this antenna pattern has to be built with observations where we know there is no rain, because if we want to detect rain, we want to set our zero level with observations that have no rain. So to do that, we collocated all our observations with independent precipitation measurements. In this case, we chose the NASA IMERGE precipitation mission, which provides estimates of precipitation for every 30 minutes with a very good spatial resolution, and also images from the geostationary satellites that provide infrared brightness temperatures that give information about the clouds. So you know if an area has a cloud or it's a clear sky. So here in the right, I'm showing you all the observations that we collect during one day on top of a snapshot of this precipitation product. So this is a zoom, and this is how we perform these collocations. So our observations are these lines here. They have different orientations, and these lines are the rays that go from the GPS to our receiver. And I'm showing here the portion of these rays that fall below 20 kilometers. That's where we expect to be sensitive to the rain. And then using these independent precipitation products, we evaluate the precipitation. So we compute the mean of precipitation within these two circles. And this is what we link to each of our observations. We can also identify if there was clouds or it was obtained in a clear sky area. So this is what I was telling you about the rays. So the rays from the GPS to the receiver cross the atmosphere. They reach very low altitudes, and here to do these collocations, we use the portion of the rays that fall below 20 kilometers, which is where we expect that the clouds are. So using this collection of collocated measurements, and after accumulating enough data, we can build these antenna patterns. These were built after, I think, 1 year of collecting data. We can put them as a function of the coordinates defined on the antenna itself. So this is from the antenna point of view, how the antenna sees these occulting GPS satellites. And here, these are the antenna patterns for the amplitude and for the two antennas, the H and V. And what you can see is this. So this is very high amplitudes, then it decreases, it increases again. This is a very characteristic sign of interferences called multipath. and these are especially strong in the H antenna. We also see how the maximum performance, it's to be expected here in the center of the field of view, but due to this metallic structure, it shifted to the left. So here we have the maximum performance of the antenna. And also we can see how part of the field of view was blocked. So we cannot collect any observation that falls in this region here. Whereas in the other side, we can collect them. So this is for the amplitude, and what's more important for us is the phase difference. So remember that they said that we build these antenna patterns using free of rain data. So, well, if these are free of rain data, we would expect that the phase difference between the H and V, it's all 0. And you can clearly see that this is not the case. So it's evident that we have to correct all our observations using these antenna patterns. And this is what we do. We correct all our observations using this antenna pattern. Here I'm showing you an example of one observation. This is the SNR and or the amplitude of the collected signal. You can see how the vertical amplitude is larger than the horizontal, so the V antenna performs better. And these are the differential phase shift measurements, so the difference between the H and V phases. And you see how before the correction, this yellow line is before the correction. And you see how when you apply this correction with the antenna pattern, this differential phase shift follows very closely the zero level. And in this case, after a certain time, so remember that this radio occultation geometry, you start from the top of the atmosphere and you go down. So you penetrate deeper and deeper. And after a certain point, there's this jump in the phase difference, which in this case is because we were crossing precipitation. So also after some time, you fall into the very low amplitude region, and it's what we call the noise level. So the observations after this time are usually discarded. So what we can do after we have corrected or calibrated all our observations, we can look for the statistics. So we correct all the observations regardless of precipitation, and we do the mean and the standard deviation based on different precipitation regimes. The one that we are looking first is the statistics of the observations where we know that there was no precipitation. And what we see, this is the black line. So this is the average of all the observations with no precipitation as a function of height. And we see how the mean follows very nicely the 0 line, which is exactly what we expect to see if there's no rain along the gray paths. This is the orange shade is the standard deviation, which I also show here. And we see how this standard deviation, it's very close to the 1.5 millimeters that we estimated before launch that would be our noise level. So we were very happy with this. And what we also see is that when you look at the mean for the profiles that were collected under certain precipitation intensity, you see how the mean moves towards the positive side, which is what we expect to see if there's rain. And even when these profiles were collected under heavier precipitation, they move even farther to the right. So that's very good news. What we wanted to do as well, instead of using at these vertical profiles, is to use some characteristic value linked to every observation. So then it's easier to compare our observations with these precipitation missions, because we can compare values with values, and so single values with single values. And what we decided to do is to do the average of every single profile between 0 and 10 kilometers. So if there's no rain, we would expect that this means 0, and then it would increase if there's rain along the gray paths. And this is what we saw. We saw that if you plot the rain rate obtained by these NASA precipitation missions, and you plot them against our observations, you see how when there's no rain, our measurements are very close to 0, and they increase as the precipitation increases. So this is very good news, and it means that polarimetric radio occultations are not only sensitive to the presence of precipitation, but it's also sensitive to its intensity. And this, so in fact, it was the main goal of the mission to demonstrate that polarimetric radio occultations were able to detect precipitation. So this is what we saw, and we saw it with less than 1 year of data. So we were very happy about that. So we also wanted to see if these observations were capturing well the well-known precipitation patterns. So, and you can see here in this plot where all the observations are grouped in different locations. You see how they follow very well these precipitation patterns that you can see in the NASA precipitation product. And something else that we wanted to explore is the vertical structure of these observations. So to validate and to demonstrate the capability of polarimetric radio occultations to sense precipitation, we used this single value, but now we come back to the more fundamental measure, and we want to explore the vertical structure. And to look at that, I'm showing you a very nice coincidence or a very nice observation that we had over a tropical cyclone. It was called Mekuno. And you can see how, so this is the infrared imagery from the geostationary satellites. You can see how these very dark regions mean that the clouds were very developed. And here you can see also the contours of the precipitation rain rates obtained with this precipitation mission. And you can see how we cross this, what we call the rain bands on the tropical cyclones. And we see how our observation starts to show very high differential phase shift signals, meaning that we are detecting the precipitation, but also in very high altitudes. So this line is the freezing level. So above this, everything must be frozen or almost frozen. So what we see is that we start to detect important signatures very high. So we wanted to explore this more. And to further explore this, we needed different coincidences or different collocations. We wanted to look for coincidences with instruments that can provide us detailed three-dimensional precipitation information. And this can be provided by weather radars. And in this case, there's a weather radar on board of the GPM Core Observatory satellite. It carries a K-band precipitation radar that provides three-dimensional precipitation structure and is very sensitive to precipitation and large frozen particles. And in addition, the satellite also carries a radiometer that obtains images, two-dimensional images with no precipitation structure, but is very useful because using the different frequencies, you know that you are sensitive to different types of particles. And you know that these different types of particles, for example, using the 166 gigahertz brightness temperature observations from this radiometer, you know that if this brightness temperature is very low, probably it's an indication of the presence of small ice crystals present in the cloud structures. So this radar, the problem is that where it scans is not very large. It's only 200 kilometers, and then you have the radiometer that scans on a region of 800 kilometers. So looking at coincidences between this satellite and our observations, we found a really nice one on a hurricane, another hurricane called Leslie. So this is a coincidence. So this is the radiometer information. These black lines are our rays, so the rays below 20 kilometers, that the region where we are sensing, and different frequencies of the radiometer indicate different types of particles. And here you see the region sensed by the radar, and the radar, it does provide these very detailed precipitation structures. So here you can see a detail of the information provided by the radar. So this is height, and this is the latitude of this area from here to here, because this is the area that the radar was sensing. So what we can do with this three-dimensional detailed information is to perform an interpolation. So we can put this grain information into our rays. So knowing where the rays have been, we can know if which precipitation particles they have crossed. We identify these liquid particles and these large frozen particles from the radar. And then we use this information to perform simulations. So we can simulate what we should be observing due to these particles. And here in the right, I'm showing our observation in black. And these are the results of the simulations. This yellow is when we simulate these liquid particles, and this shade here is the simulation using the ice particles. Remember, these are big ice particles that are seen by the radar. And what we see is that in addition that there's a lot of uncertainty because the simulations with ice are a little bit tricky, but this would fall into realistic simulations. What we see is that using this information provided by the radar, we cannot reproduce our observations. So what we have to do is to look at the big picture. And well, first, let me show you another example. It's another example where we had these collocations with the radar and also with the radiometer. Again, we have interpolated the values from the precipitation and the big ice particles into the radio occultation rates. We perform these simulations, and again, we see that we cannot explain these big signatures in the upper layers of the cloud. So, looking at the big picture, what we have to do is to look for another radar. So, unfortunately, this other radar that I am showing you here is not operational anymore, but it was operational before the launch of the PAZ satellite, and we have coincidences between these two radars. So this is the radar that we are using, and I was showing you before. It operates at a frequency of 13 gigahertz, and this other radar was operating at a frequency of 94 gigahertz. Therefore, it's more sensitive to the smaller particles. So using coincidences between these two satellites, we can see the whole picture if of what is going on in one of these heavy precipitation events. What we see is that with this radar, the GPM radar, we see very detailed information about the precipitation and some of the frozen part of the cloud. But when we look at the same scene as seen by the CloudSat radar, we see much more structure that is not captured by the GPM radar. So what we have done was to build some lookup tables using the coincidences between these two radars. So for every of these observation, we built a lookup table of what the other satellite would have observed if it was observing the same area. And with these lookup tables, what we can do is to, based on the GPM radar observations, account for the information about the smaller ice particles that we could have seen if there was a collocation with this other radar that operates at a higher frequency. So using these lookup tables, we can include this information about the ice, perform the simulations, and what I'm showing you here in the right side is that when we compare the observation in black with the simulations using the information in the GPM radar, we cannot explain the upper layers, but when we account for the ice information, we can match much better the observations, and therefore we can explain why we have these strong signatures in the upper layers, and that is because we are also sensitive to the smaller frozen particles that are present through the whole vertical cloud structure. So I'm showing you a couple more examples. So this is what happened when we find one of these collocations. We use our lookup tables based on the information from this radar called GPM to build or to infer what the other satellite would have seen. And we can interpolate this information into the rays and then perform the simulations, and you can see how we can explain these upper layers. This is another collocation. Actually, this is the first one with a hurricane. We can do the same using these lookup tables. Now the simulations match the observations much better. And finally, another case where we had a coincidence with this radar. With only the radar, we cannot explain everything, but when we account for the ice particles, we can explain our observations. So we can say that we are sensitive to precipitation, we are sensitive to frozen particles, and therefore we have this full picture of the cloud. So we are sensitive to the whole cloud structure. And this is just my last slide, and I wanted to show you how can we use this information. right? I said that it was very valuable, the fact that we can provide this joint thermodynamics and precipitation information. So what we can do is to use all the observations that we have collected with the PAZ satellite. We group them according to the differential phase shift measurement, which is a proxy for precipitation or heavy precipitation. And then we see how the different groups, how these relative humidity in this case, but this applies for all types of moisture, how they change as a function of height. And we've done with this for the tropical oceans separated by different basins, and also for the tropical land. And what we can see is that one of the relevant results that we can obtain with this is, for example, that when we compare the heavy precipitating cases with the no precipitating cases, according to our observations, we can see how the maximum difference in the amount of moisture and the amount of humidity is in the free troposphere, is not in the lower layers, which is something that you could think. And this is even more noticeable over ocean than over land, because over land, the lower layers plays a more important role on how these convective events are driven. So this is just an example on how we can use these data sets. So yeah, arriving to the summary and conclusions of this talk. So the ROHP-PAZ experiment is a proof of concept mission that it's testing the polarimetric video occultation concept for the first time from space. It was launched in February 2018, and our experiment was activated soon after. The on-orbit calibration was required due to this metallic structure that was installed in front of our antenna. But even with this problem that we had with this metallic structure, soon after the activation of the experiment, we already saw that the polarimetric differential phase shift observables are sensitive to precipitation. The noise and detectability levels are consistent with the pre-launch studies that we performed. And we can also see that the vertical structures of these observations reveal sensitivity to frozen particles, and therefore we are able to sense the whole convective cloud structures. And these allow us to provide these joint thermodynamic and precipitation observables that are potentially very useful for study the precipitation processes. And yeah, that was all. And thank you very much. I'm going to answer any question you could have.
Thank you, Ramon. Excellent talk. It was very interesting to see other concepts apart from astronomy, and I'm passionate about climate, so that was very interesting for me. I don't know if somebody wants to ask a question, please raise your hand or just speak up. No questions for Ramon? I have a few in the meantime. So first, I guess it must have been really discouraging when you learn about the metallic plaque and that it was causing a problem on your calibration. How did you feel about that? And could you have any? Could you complain or could you get any reward for the company that created that distortion?
Actually, no, we could. I don't think we could do anything about it. And yeah, it's true that in the beginning it was very discouraging because we found out about that before the launch. So we were not expecting the results that we finally got. So at the beginning it was, wow, what are we going to do now? But at the end it was not that much of a problem. We could solve it with this calibration. So so it was kind of okay at the end. But
so I have a doubt about the calibration. You use prior other measurements of rain to calibrate your instrument. So if I understand correctly, the main difference between those measurements and your measurements are the fact that you have the height information as well, right? And could the calibration be affected somehow because you're calibrating it with only superficial values?
So first, we are not calibrating our measurement. So we are kind of calibrating. So we use the information to separate our data in groups. And then we use the groups that are not affected by precipitation to perform the calibration. it's different from other observing systems where they actually calibrate their measurements based on other measurements. In this case, this is not what we are doing. However, you're right about this vertical structure. So we are using this surface precipitation information that provides the precipitation on the surface. And it's true that you could have precipitation or very well developed clouds above this area, but it's actually not precipitating. This could be the case, but that's why we also use the geostationary infrared imagery, which tells about the clouds. So we are using data that has no precipitation, but has no clouds as well. So we are kind of very sure that there's no precipitating structures around the area that we are sensing.
Okay, and basically your calibration, what you want to do is to have this pattern that you show has to be clean, uniform, right?
Yes, in theory, ideally that would be, so there was no interference and it was done using only free of rain data. You should see a very smooth, centered at zero antenna pattern, but this is not. This was not the case. And in fact, this is ideally, but usually these antenna patterns are never close to zero. But you usually measure these antenna patterns before the launch, and you can use that for the calibration. But since they had to include this metallic structure, we had to do the on-orbit calibration. That was a little bit more challenging.
Okay. Are there any questions? Somebody else wants to ask? If not, I have other questions because I really like the topic. So do you sell or do you share this data with other parties? What do you use them for?
Yeah, this data is publicly available from our website, that it's part of the Institute's website. And it's also available from the people who is doing the first processing. So you can get this data from different places, and yeah, it's completely free and publicly available. I think you only have to register, but then you are able to download the data. And
do you know if some who is using the data, or what can it be useful for? Maybe for predicting weather, or?
Yeah, currently we know that not many people is using it. We are aware that it's a very new measurement, and usually the community is a bit scared of using new things. But we are, so our main work now is to promote the use of this data. And as I said, I think that so we are still working on improving these retrievals and improving the quality of these profiles. But I think that this could be very useful for study these deep convective events. So these deep convective events happen mostly in the tropics, and for example, over ocean, you cannot. You have to rely on satellite platforms that measure the thermodynamics. Most of them cannot penetrate into this deep convective system, so you have no information about the moisture and the temperature inside these storms. And also it's very complicated to observe them globally. So maybe you can set up an experiment somewhere, but to obtain the global view, it's difficult. So we expect that this, and also provide this vertical structure. It's very fine vertical structure from this measurement. So I think these are the strong points for this measurement, and we hope that in a few years the community is using these products. And also the fact that you don't lose information when you switch from the standard radio occultation to the polarimetric one, you can still retrieve these thermodynamic profiles, right? Mm-hmm. So that's maybe something that we need to promote more, so that the next satellites that want to carry a radio occultation platform, maybe they can use a polarimetric radio occultation platform instead of the standard one, because you win this precipitation information that you cannot obtain with the standard technique.
That's great. So
can I add? Hi, this is Estelle. Can I add that some of these commercial companies that currently have radio occultation satellites orbiting, the Earth. Some of them are already planning to change their systems, so very soon they also can provide polarimetric radio occultation data, and that would be a great achievement for us, because that would also facilitate a wider community getting interested and studying these data sets and technique.
Okay, that sounds very cool. So best of luck. Is there any final comment or any final question? If not, I want to thank Ramon again and wish you all a happy weekend.
Thank you. Thank you very much.
See you soon. Bye.
Bye bye. Bye bye.
Bye.